Math 2414, Taylor and Maclaurin series video 3. Let's get that fixed. Not E. Video 3, Maclaurin series for f of x equals e to the x. By the end of this series of videos, there will be several Maclaurin series that you should memorize, not just for this class, but for classes in the future, especially if you take differential equations or some engineering mathematics classes. Do not move forward without memorizing series when I tell you you need to have this series memorized. This will be one of them. All right, so we're going to build the Maclaurin series for f of x equals e to the x. But just a reminder from the previous video that a Maclaurin series for a function is a series of this form. F of x equals the sum of from n equals 0 to infinity of the nth derivative evaluated at 0 divided by n factorial times x to the n. So to calculate the series means to come up with the coefficients. So we have to figure out what the nth derivative evaluated at 0 over n factorial looks like for n equals 0, n equals 1, et cetera, et cetera, et cetera. So in order to do this, we need to know a bunch of derivatives. Now, luckily, we have one of the easiest things in the world to take derivatives of. That would be e to the x. Let's go ahead and write out what this series would look like. If we start with 0, n equals 0, then we're taking the 0th derivative, which is the original function, evaluated at 0, over 0 factorial times x to the 0. If we let n equals 1, that means we take the first derivative, evaluated at 0, over 1 factorial plus x to the first. I know I don't need the 1 there. And let's take it out to 4 terms. The next one would be the n equals 2 would be the second derivative, evaluated at 0, over 2 factorial times x squared. And it's not hard to pick up on this pattern. The third derivative, evaluated at 0, over 3 factorial times x cubed. I think I have room for one more. Plus the fourth derivative. Now, once you get beyond 3, it's usually prudent to just write the regular number in parentheses to indicate the order of the derivative. The fourth derivative, evaluated at 0, over 4 factorial times x to the 4th, plus dot, dot, dot. All right, so let's get to cracking here. Now, luckily for all of these, derivatives are equal to 0. In other words, because our function is e to the x, we know that the nth derivative is equal to e to the x for n equals 0, 1, 2, dot, 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 dot. So that makes this one a little easy. Makes it really easy because all of the functions and derivatives are e to the x. So all of the derivatives are evaluated at 0. So the nth derivative evaluated at 0 is e to the 0, but e to the 0 is just 1. That means that every derivative here can be replaced in this example with just the number 1. So let's do that. All right. Okay, so we have 1 over 1 factorial. Excuse me, 1 over 0 factorial. The 0 factorial is 1. We have 1 over 1. Let me highlight where I'm talking about here. This is equal to 1. We just said that here about all the derivatives, even the 0th derivative. This is equal to 1 by definition. And that's equal to 1 because anything to the 0 power is 1. Well, let's not go down that path again. So we have 1 over 1 times 1. So that first term just collapses all the way down to a piddly little 1. Plus. All right, let's move on to the next one. This is equal to 1. Remember, all the derivatives are equal to 1 in this problem. 1 factorial is equal to 1. And why do I have a plus there? I shouldn't have a plus there. It's times x to the first. Speaking of which, we have 1 over 1 times x to the first. That was supposed to be highlighted, but that's okay. 1 over 1 times x to the first is just x. So let's get rid of this, and let's write x. For the rest of them, let's go ahead and evaluate the factorials. In the next fraction, right here, The numerator is 1, the denominator is 2 factorial. 2 factorial is equal to 2. So we have 1/2 x squared. On the next one, the derivative is 0. 3 factorial is 6. So we have 1/6 x to the third. On the next one, we're going to have 1/4 factorial. 4 factorial is 24 times x to the fourth plus ... And if we wanted to represent a generic term, we know the numerator is going to be 1. We know the denominator is going to be n factorial times x to the n. So let's write this a little bit more cleanly on the next page and replace f of x with what it equals, which is e to the x. So e to the x is equal to the sum n equals 0 to infinity. The nth derivative evaluated at 0, but in this case it's always equal to 1 over n factorial times x to the n. That's it. And if we were to expand it, it would be 1 plus x. Let's write it as x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus ... And I guess if I'm going to write it like that, then I can go back in here and put the x to the n on top of the n factorial. Now, this is a Maclaurin series, so it's centered at 0. Let's talk about where this is going to converge. And then we will come up with a pretty interesting fact. As far as convergence, the interval that it converges on, we could do a variety of things to show that the series converges. For example, we could do the ratio test. Remember, this is assuming it's converging, but I want to verify that it converges real quick. We take the limit as n approaches infinity of the absolute value of the next term, which would be x to the n plus 1 factorial, times the reciprocal of the current term, n factorial over x to the n, and then clean this up. Let's start with the x's. This cancels all but one of them. And as far as the n factorials, without rehashing that story, this n factorial will knock out everything except the n plus 1. So let's see where that puts us. We have an absolute value of x, which is independent of n, so we can pull it out of the limit, times the limit as n approaches infinity. We're left with the n plus 1, but it's in a denominator. Technically, it's inside an absolute value, but it really won't matter because that limit is 0, and 0 times anything is 0. So our limit in the ratio test is 0, which is less than 1, which means we get convergence for every value of x. So now we know it converges all the time. Doesn't matter what x equals. But here's something else that's going to be handy in a little bit down the road. We now know that this converges for all x's. So we don't have to worry about what x equals. But something we're going to run across in a little bit, this may seem like it's completely out of nowhere, is this limit. Limit as n approaches infinity of x to the n over n factorial. It's going to be handy to know this limit. We can't use L'Hopital's rule because the denominator is not a continuous function. It's just n factorial. It's a discrete function, if you will. So we can't take L'Hopital's rule, even though both sides go to infinity. So can we say something about this limit? Well, yeah, in a backwards sort of way using the test for divergence. The test for divergence says if this limit is not 0, then the series diverges. But guess what? The series converges. That means this limit can only be one thing. It must be 0. We could say by the contrapositive for the test for divergence. Basically, the test for divergence says if the limit is not equal to 0, that implies that the series diverges. But without discussing symbolic logic like we did in a previous video, if this statement is true, so it's contrapositive. Contrapositive means we switch the order and negate both halves. So we can say that if the sum converges, that implies that the limit has to equal 0. So since we already know that the sum converges all the time, we know that that limit has to equal 0, the one on the bottom, the limit of the individual term. It's kind of a backwards way of using the test for divergence, but it is a sneaky way to show a limit is equal to 0 by showing that the sum converges all the time. So we're going to need that limit later. Keep that in mind. All right, so this is a series that you need to know. You need to know that e to the x is equal to all this. I can't stress this enough. As you move forward in your math studies, whether they're math or engineering or physics, you need to know this, and you need to know it converges for all x. So what's the nifty little thing I wanted to show you? Well, if it converges for all x, then it converges for x equals 1. So the nifty little thing I wanted to show you is if x equals 1, then we get the following statement about the number e. E is equal to 1 plus 1, remember x is equal to 1, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial. In other words, e is equal to the sum of the reciprocals of the factorials from 0 to infinity. So it's a nice little way to approximate the value of e. You just keep adding reciprocals of factorials. So that's a nice little thing to know, this little statement about the number e. Of course, you could put the first two ones together and just call it 2, but using direct substitution of x equals 1 into the Maclaurin series for e to the x gives us that. So I'm going to close this video by saying the same thing I said a minute ago. You need to memorize this, that e to the x is equal to, and I guess I should highlight that sum in the middle, that e to the x is equal to this sum, which is that infinitely long polynomial. Memorize it, memorize it, memorize it. I can't say this enough times. Don't go to another class and say, I didn't know that e to the x is equal to that, because I'm telling you, you need to.